Gallatin Range, Montana Territory, November 12, 1872. A pre-winter upslope system reported from Fort Ellis delivered 18 inches of snow in 14 hours, with gusts recorded above 70 miles per hour along exposed benches. Frontier cabins built quickly, 6 to 8 inch lodgepole logs, unbraced door frames, rafters set 30 to 36 inches apart, often racked under the first serious wind. Roof failures were common. Quartermaster reports from the same decade list 20 to 25 pounds per square foot snow loads collapsing unbraced spans under 12 feet. One cabin on a small ridge at 6,400 feet should have matched the pattern. Instead, it held. Its door remained square, ridgepole unbowed, corner joints unspread. The key feature was a technique noted sporadically in survey camp outbuildings and Scandinavian settler cabins: a central stiffback spine wall, a vertical hewn beam tied into plates, header, and opposite corner posts to force loads to travel through the entire shell. The frontier rarely rewarded craft over speed. This storm and a later bear incident showed that the math, not the muscle, decided which structures lasted a season and which did not. Morning frost on wall plates, the silent warning of altitude's demand, Upper Trail Fork, Gallatin Range, June 14, 1872. Thin morning frost clung to unroofed wall plates where they lay stacked beside a shallow foundation trench. The frost should not have been there in mid-June. Its presence marked altitude, exposure, and the climate reality that most trappers building at lower elevations never confronted. Ridge cabins faced wind speeds that doubled valley readings. Temperature swings of 50 degrees in 24 hours expanded and contracted log joints with brutal efficiency. Summer could freeze a water bucket. Winter could split green wood. Most trappers expected a 4-day shack. Ridge exposure demanded engineering they rarely practiced. The landscape offered lodgepole pine, 6 to 10 inches in diameter, straight stems but frequent spiral grain that weakened notch bearing under lateral load. The Hayden survey notes described thin-soiled benches, poor root anchoring, and wind scour around exposed stands. A solitary builder could haul logs only from within half a mile to 1 mile. Beyond that distance, drag friction consumed a full day per log. Fort Ellis weather logs from 1870 to 1873 confirmed the baseline. Summer ridge winds of 40 to 50 miles per hour were normal. Temperature swings ranged from 35 to 90 degrees Fahrenheit within a single day. Occasional June snowfalls delivered wet density up to 20 pounds per cubic foot, loading roofs before the season should have turned. The tool set was limited by pack animal economics. Hand tools only: felling axe, saw, broadaxe, 1-inch auger, small adze. No pack animals meant roof shakes had to be split on site. The build window was constrained by trapping cycles. Completion was required by mid-July when trap lines demanded attention. Period documentation from Hayden survey field notes warned, benches drift from west. Structures set cross to wind show drift scour beneath logs. Early territorial notices listed collapsed ridge cabins after summer storms. The cause and effect relationship was documented but rarely heeded. Thin logs plus high wind plus temperature cycling equaled predictable racking. The walls could be raised in 4 days, but the wind could undo them in 4 hours. Warped door frame. The geometry of failure made visible Bozeman Trail corridor. Compiled records, 1868 to 1873. A freighter cabin door hung 10 degrees out of square, hinge pins nearly sheared from lateral stress. The door opening itself had become the pivot point for the entire structure. Wind pressure pushed against the door wall. With no interior bracing to share the load, the wall flexed. The door frame, already weakened by the 30 to 40% loss of shear resistance created by the opening itself, deformed first. Expectation held that saddle-notched corners were good enough. Outcome records showed chronic failures. The door frame functioned as a hinge line under wind shear. The door opening removed structural continuity on one wall. Under sustained horizontal pressure, the door side became the rotation axis. U.S. Army Quartermaster specifications from 1871 stated clearly, "Door wall must contain a tie beam if span exceeds 10 feet." The specification existed because the failure mode was well understood in military construction. It was ignored in civilian trapper cabins where speed trumped structural planning. Unbraced roof spans presented the second failure mode. Anything over 10 to 12 feet without interior support sagged under snow. Snow density in storms ranged from 20 to 25 pounds per square foot equivalent uniform load. By January, sagging ridge poles created gaps between shakes, allowing heat loss and water infiltration. The sag was cumulative. Each storm added load. Each load increased deflection. Deflection opened gaps. Gaps reduced thermal efficiency. Corner spread was the third documented failure. Road crew bunkhouse records showed 1 to 2 inches of lateral drift by midwinter. Spread opened chinking gaps. Heat escaped. Fuel consumption increased by 1 to 2 extra cords per winter to compensate for structural inefficiency. The human and logistical consequences were documented in operational records. Section houses failing caused route delays. Supply cabins collapsing cost settlers entire season's rations. Lives were lost when shelter failed during storms. Sources included U.S. Army building circulars from the 1870s and railroad section house inspections from Gallatin Valley in 1871. The weakest point was not the roof. It was the unbraced rectangle around the door. Hewn 6x6 post. 3 traditions converging in one beam, Northern Rockies and Scandinavian settlement clusters. 1860s to 1870s. A hand-hewn 6x6 post leaned against a wall in a Swedish settler cabin near the Dakota border. Tool marks remained sharp from winter dryness. The post had been shaped with deliberate precision, 4 flat faces meeting at 90-degree angles, ready for installation as a center tie wall support. Expectation held that trapper cabins stood alone in method. Outcome showed 3 building traditions converging on the same load path principle. Scandinavian settler practice included center tie walls under sod roofs. A Dakota Homestead ledger from 1873 mentioned middle post fastened to plate. The structures were built to resist snow loads, double those typical in Montana. The logic was straightforward. Distribute roof load to an interior point, preventing the walls from spreading outward under compression. Mining camp carpentry provided the second source. Virginia City outbuildings used mid-wall posts to prevent machinery vibration from racking walls. Belmont Mill construction notes specified, center brace to check wall drift. The mills required dimensional stability. Misaligned machinery caused operational failures. Interior bracing solved the problem. Indigenous structural logic offered the third parallel. Crow and Shoshone lodge frames employed internal braces combined with compression rings. The purpose was preventing oval distortion under wind. Lodge covers generated significant wind pressure. Without rigid internal structure, the frame flexed. Ethnographic records from the U.S. Bureau of Ethnology documented the engineering in field bulletins with detailed diagrams of lodge anchoring systems. Transfer to trapper workflow was practical. One man could hew a stiffback in 3 to 4 hours and install it in 2 to 3 additional hours. The labor investment saved seasonal realignment work that consumed far more time over winter months. The principle underlying all 3 traditions was identical. No wall should stand alone against lateral force. Load paths had to travel through the entire structure, not concentrate at joints. Whole shell stiffness outperformed isolated joint strength when materials were limited by transport and tool constraints. 3 traditions. 1 rule: no wall should stand alone against the wind. Bark curls from the broadaxe, evidence of intentional bearing surfaces, Gallatin Range, June 22 to July 3, 1872. Bark curls piled knee-deep beside the foundation trench where the broadaxe had shaped log faces. Squared logs gleamed where the blade had removed sapwood and created flat bearing surfaces 1 to 1.5 inches wide. Each log face contacted the next with precision. The work was slow. A round log could be notched and stacked in 20 minutes. A squared log required 2 hours of careful hewing. Expectation favored fast shelter. Outcome showed every step revealing intentional load path thinking. The footprint measured 10 feet by 12 feet. 9 courses of logs would rise to create walls. The foundation consisted of flat stones direct set into shallow trenches, typical for ridge terrain where frost heave was minimal due to wind scour preventing deep snow accumulation. Logs were squared to create consistent bearing. Round logs contacted each other at single points. Squared logs contacted across their entire width. The difference determined how load transferred through the stack. Point contact concentrated stress. Full surface contact distributed it. The door opening measured 32 inches. Hand-forged strap hinges came from a smithy near the Gallatin settlements, common in the region after 1870 when small forges served scattered homesteads and trapping camps. The door frame represented the primary structural weakness. The header spanning the opening was free-floating relative to the back wall unless tied through the structure. The roof system used a single ridgepole spanning 10.5 to 11 feet. Rafters were spaced 24 to 30 inches apart, notched to sit on the top wall plates. Shakes were split from straight grain lodgepole, 18 to 24 inches long, 3/8 inch thick. The split faces shed water better than sawn lumber and required no mill access. Structural vulnerabilities were present from the start. No interior tie meant walls acted independently under lateral load. The door wall would become the pivot plane under wind. The math was simple. Horizontal force times lever arm equaled rotational moment. Without a counterforce, rotation was inevitable. Before the first frost hit the notches, the cabin had already inherited a flaw. Freshly hewn stiffback post, one beam rewriting structural behavior, Gallatin Range, July 4, 1872. A freshly hewn 6x6 post stood plumb beside a dirt chalk line scratched into the cabin floor. The post rose 6 feet from floor to the planned height of the interior tie plate. Its 4 faces showed clean Broadex facets, no twist, no bow. The timber had been selected for straight grain, cut from a tree growing in dense stand conditions where competition forced vertical growth without branching. Expectation held that no trapper wasted time on interior posts. Outcome showed this one adding 3 critical tie points that changed the math of the entire structure. Specifications were precise. The post positioned 6 feet from the door, roughly cabin center. A tie plate would be fixed at 6 foot height, running from door header through the stiffback to the opposite corner post. Knee braces, angled supports connecting post to plate, would be pegged with 1-inch trunnels, hardwood dowels driven through auger holes. The structural function was load redistribution. The stiffback converted the door wall from a weak hinge line into part of a shear-resisting plane tied to the opposite wall. Wind force pushing on the door wall now had to overcome the stiffness of the entire cabin box, not just the strength of door frame joints. Snow load on the ridgepole now bore on 3 support points instead of 2 end walls. The center support prevented ridge sag, which in turn prevented shake gaps and maintained roof plane integrity. Labor and tool requirements were modest. Hewing consumed 3 to 4 hours. Assembly required only an auger and mallet to set trunnels. Zero reliance on nails was deliberate. Nails loosened under shrinkage as logs dried and contracted. Wooden pegs swelled slightly when they absorbed moisture, tightening their grip. The joint improved over time rather than degrading. Documentation existed in mining camp records. A Belmont Mill construction note specified, "Center brace fitted to restrict wall drift." The practice was known in industrial building where dimensional stability mattered for operational reasons. One post changed the behavior of every log around it. Hairline crack in chinking, the visible signature of invisible force, Gallatin Range and Fort Ellis weather logs. Winter, 1872. A hairline crack appeared in the chinking along the windward wall where clay had pulled away from the log surface. The crack was narrow, barely visible in dim cabin light, but its presence marked the boundary between elastic deformation and structural failure. Every structure flexed under load. The question was whether it returned to original geometry or accumulated permanent distortion. Expectation held that winter loads built slowly. Outcome showed loads spiking abruptly and unevenly. Wind profile data from Fort Ellis documented sustained speeds of 45 to 60 miles per hour as normal for ridge exposure. Gusts above 70 miles per hour were recorded multiple times each winter. The door wall took direct shear because it faced into prevailing northwest wind. Horizontal pressure created a bending moment at the base of the wall. Without interior bracing, the wall acted as a cantilever beam, maximum stress at the foundation. Snow loading added vertical compression. Wet snow delivered 35 to 40 pounds per square foot. Drift asymmetry created uneven load distribution. Lee side drifts accumulated to 3 or 4 feet, while windward sides remained scoured. The ridgepole bent under asymmetric load, creating torsional stress in the end walls. Log and joint behavior was temperature dependent. Logs shrank 1 to 2 inches in diameter as they dried during the first winter. In unbraced cabins, shrinkage opened gaps and allowed walls to settle unevenly. Stiffback cabins showed less than 3/4 inch seasonal drop because the interior tie forced all walls to move together, maintaining alignment. Stiffback effects were measurable. Doors remained square. Plates shared bending load, preventing concentration at weak points. Ridge deflection was minimized. Hinge bind, the jamming that occurred when door frames racked out of square, was drastically reduced. Period documentation confirmed the pattern. The Bozeman Weekly newspaper reported in January 1872. Sheds downed by drift weight. The failures were predictable, seasonal, and avoidable. Wind loads doubled at the ridge, but the cabin's resistance multiplied. Low smoke line from stovepipe, thermal efficiency made visible ridge cabin operations, winter 1872 to 1873. A low smoke line rolled from the tight stovepipe cap, gray against white sky, settling quickly in the cold, dense air. The smoke's behavior indicated efficient combustion and minimal draft loss. Heat stayed inside the structure instead of escaping through gaps around doors, windows, and eaves. Expectation held that winter heating was fuel-intensive, regardless of construction. Outcome showed structural precision cutting fuel demand nearly in half. Average fuel use for ridge cabins typically reached 3 to 4 cords per winter. A cord measured 4 feet high by 4 feet wide by 8 feet long, roughly 128 cubic feet of stacked wood. Cutting, splitting, and hauling one cord represented 2 full days of hard labor. 4 cords meant 8 days of work that produced no food, no income, no advancement toward proving a homestead claim. The stiffback tied cabin showed fuel savings of 1 to 1.5 cords per winter. The reasons were structural. The door wall did not rack, so smaller drafts formed around the jamb. Chinking held without seasonal repacking because walls maintained alignment. Shakes seated more evenly due to reduced ridge sag, preventing gaps that allowed heat to escape through the roof plane. Ventilation pattern mattered for both heat retention and smoke management. A high gap under the ridge peak allowed smoke and hot air to exit. Low intake near the door provided fresh air for combustion. The flow pattern was self-regulating. Hot air rose naturally. Cold air sank. The cabin breathed without creating cross drafts that stripped heat from living space. Period comparison existed in railroad section house maintenance ledgers from 1873. Structures built with center tie walls showed identical fuel savings. The pattern was repeatable, documented, and tied directly to structural integrity, preventing air infiltration. A single brace conserved more heat than a week's cutting could replace. Willow rib compressed in lodge ring, engineering hidden in plain sight, Crow and Shoshone regions, ethnographic records, 19th century. A willow rib was cinched snug into a lodge compression ring, bark still on, green wood bent to the required curve. The rib was one of dozens arranged in a conical pattern, each one held in place not by individual strength, but by the collective geometry of the ring. Remove the compression ring and the lodge collapsed. Maintain the ring and the structure resisted wind that would flatten a simple tipi. Expectation held that frontier cabins and indigenous lodges differed entirely. Outcome showed they relied on the same engineering logic. Lodge structural method used internal braces to prevent deformation. The compression ring, a circular band at the lodge's widest point, kept all ribs under equal tension. Wind pressure tried to push the lodge into an oval. The ring resisted by converting bending stress into hoop stress, which the circular geometry handled efficiently. The principle was ancient, documented in structures from yurts to igloos to wattle and daub roundhouses. Parallels to spine wall cabin construction were direct. Both created whole shell stiffness. Both prevented racking under lateral load. Both used internal members to force loads to travel through the entire structure rather than concentrate at weak joints. Ethnographic sources included U.S. Bureau of Ethnology bulletins, published in the 1880s, compiling field observations from the previous 2 decades. The bulletins contained detailed diagrams of lodge anchoring, compression ring attachment methods, and wind resistance testing conducted by measuring deflection during storms. Transferable insight was clear. One-man cabins and multifamily lodges solved identical problems. Stiffness beat mass when materials were limited. A thin structure properly braced outperformed a thick structure poorly connected. The principle applied whether the material was willow, lodgepole pine, or milled lumber. Cultural exchange rarely appeared in written records, but practical knowledge transferred through observation. A trapper seeing lodge frames during winter trading visits understood structural logic even without technical vocabulary. A willow lodge and a pine cabin solved wind shear with the same geometry. Rafter dust filtering through shake seams, the moment before failure or proof, Gallatin Range, November 12 to 14th, 1872. Rafters trembled under sustained gusts, transmitting vibration through the entire roof structure. Dust filtered from shake seams where wind pressure tried to lift the roof plane. Each gust created uplift on the windward slope and suction on the lee slope. The forces were opposite, but the net effect was identical, trying to separate the roof from the walls. Expectation held that unbraced cabins twisted by midnight. Outcome showed the spine wall cabin staying functional. Weather numbers came from Fort Ellis records. 18 inches of snow fell in 14 hours. Gusts exceeded 70 miles per hour. Drifts accumulated to 3 or 4 feet on the lee side, where wind deceleration allowed snow to settle. The storm ranked among the most severe early-season events in territorial records. Predicted deformation based on unbraced cabin performance suggested 1 to 2 degrees of wall lean by storm end. Actual measurement showed less than 1 degree. The door remained operable. No binding occurred. The threshold stayed level. A candle flame near the jamb showed minimal draft. Load path confirmation was visible in subtle details. Ridge sag measured less than 1/4 inch across the 11-foot span. No corner spread occurred. Chinking remained seated. The structure behaved as a unit, not as 4 independent walls with a roof laid on top. Comparative failure provided context. A stage station south of the range reported door jamb drift failure the same week. The newspaper notice was brief. Station cabin damaged by storm. Door inoperable. Crew relocated to Bozeman pending repair. The failure mode matched predicted behavior for unbraced construction under identical load conditions. The storm provided proof that the engineering worked under extreme conditions. Theory became verified practice. The stiffback was not decorative. It was load-bearing, structurally essential, and the difference between a cabin that sheltered occupants and one that forced evacuation. 2 cabins in the same storm, only one stayed square. Bare claw marks on door slab, 300 pounds of leverage applied cabin site. April 1873. Fresh claw marks gouged the lower door slab in parallel grooves, each one a 1/4 inch deep. The mark started 18 inches above the threshold and ran downward at an angle, showing where a black bear had pushed low on the door, trying to lever it open at the hinge side where mechanical advantage favored the attacker. Expectation held that a 300-pound bear could lever open a frontier door in minutes. Outcome showed load passing through the brace and distributing across the entire wall system with no failure. Bear mechanics were well understood on the frontier. Bears pushed low toward the hinge side, applying 300 to 400 pounds of lateral force. The strategy exploited the door's geometry. Force applied far from the latch created maximum torque on the hinge pins. In typical cabin construction, the hinges were fastened with screws or nails driven into the doorframe. The fasteners provided the only resistance to lateral load. Typical failures followed a predictable sequence. Hinge screws tore out first. If the hinges held, the jamb split along the grain. If the jamb held, the door itself fractured at the hinge mortises. One component failed, and the door was compromised. Stiffback load transfer created a different failure path. The door header was tied to the stiffback through the interior plate. The stiffback was tied to the opposite corner post. Force applied to the door had to overcome the stiffness of two walls acting together, not just the local strength of hinge fasteners. The load distributed across the entire structure instead of concentrating at attachment points. Observed outcome was documented by physical evidence. Hinges remained intact. No mortise splitting occurred. Surface damage was superficial. The door functioned normally after the incident. Period analog existed in Yellowstone Ranger accounts from the 1880s describing bear lever failures on patrol cabins. The documentation confirmed that unbraced doors failed regularly under predator pressure. Predator force proved what the storm suggested. Stiffness outperformed mass. Straight edge against jamb, precision measured after the test ridge cabin, July 1873. A straight edge laid against the door jamb revealed deviation under 1/8 inch across the full 6-foot height of the frame. The measurement confirmed what daily use had already demonstrated. The door operated smoothly. No hinge bind occurred. The latch engaged without forcing. The structure had returned to its original geometry after a winter of wind, snow, and temperature cycling that should have racked the frame permanently. Expectation held that winter shrinkage demanded full rechinking and realignment. Outcome showed minimal maintenance needed. Structural metrics documented the performance difference. Ridge drop measured less than 1/4 inch across the 11-foot span. Corner drift was negligible, well under 1/2 inch at any joint. No hinge realignment was required. The door that had been installed in July 1872 still functioned perfectly 12 months later. Comparison cabins provided context. Nearby unbraced structures showed 1 to 2 inches of corner drift and misaligned doors requiring removal, frame correction, and rehinging. The work consumed 15 to 20 man-hours per cabin. That time represented 2 to 3 full days of labor that produced no food, cut no firewood, and advanced no other survival tasks. Maintenance math was straightforward. The stiffback cabin required sweeping, minor chinking inspection, and routine weatherproofing. Total time, 3 to 4 hours. Savings, 15 to 20 hours of structural repair work. The labor efficiency compounded across seasons. A cabin requiring minimal maintenance freed time for productive work. Period documentation supported the pattern. Road gang bunkhouse assessments from 1874 showed identical benefits in brace structures. The Railroad Maintenance Division tracked repair hours per structure type. Cabins with center bracing required 30 to 40% less seasonal maintenance than unbraced equivalents. The assessment proved that engineering decisions made during construction determined operational efficiency for years afterward. Building correctly the first time was faster than building quickly and repairing constantly. Where others rebuilt, this cabin swept out dust and stayed standing. Ledger line reading, center brace fitted to plate. Method entering the record Montana Territory, 1873 to 1885. A ledger line in a county building inspector's record read, center brace fitted to plate. The notation appeared without elaboration, a single line in a column listing structural specifications for a stage station outbuilding. The inspector had seen the feature, recognized its function, and recorded it as standard practice worth documenting. Expectation held that isolated frontier innovations remained isolated. Outcome showed widespread adoption. Adoption patterns appeared across multiple industries. Stage stations incorporated spine walls in station houses where door traffic created structural stress. Railroad section houses adopted the method after maintenance records showed fuel savings and reduced repair schedules. Mining outbuildings used center braces, where machinery vibration threatened to rack walls out of square. County records listed mid-wall brace in building descriptions after 1875. The terminology varied, but the feature was consistent. A vertical post positioned near cabin center, tied to roof plate and door header, functioning as an interior shear wall. Settlement logic drove adoption. Reduced fuel use meant fewer man-hours spent cutting wood. Increased survivability of ridge cabins meant claims could be proved in locations previously considered too exposed. Lower maintenance requirements meant labor could be allocated to productive work instead of constant structural repair. Documentation appeared in multiple sources. An inspector's note from 1876 stated, "No rake or shift after storm." The language was technical. Rake referred to wall lean. Shift meant corner spread. The absence of both confirmed structural integrity under load. The diffusion was organic, driven by observed performance rather than formal dissemination. Builders saw cabins that survived storms. They asked questions. They adopted techniques. The knowledge spread through practical demonstration, not written instruction. The method's value was proven by its adoption across trades that had no connection except the shared need for structures that resisted lateral load. Stage operators, railroad maintenance crews, and mining engineers independently reached the same conclusion. The spine wall worked. A single post entered the ledgers of 3 different trades. Weathered stiffback still tied to decayed roof plate. What endures after everything else fails. Regional span. 1870s to 1890s. A weathered stiffback post stood vertical in the remains of an abandoned cabin, still tied to a decayed roof plate. The logs had rotted at the notches where moisture accumulated. The shakes had blown away. The door was gone, but the stiffback remained, holding the geometry of the structure even as the structure itself dissolved. Expectation held that frontier buildings died quickly. Outcome showed braced cabins lasting decades longer. Longevity data came from building inspections and county records tracking structure abandonment. Spine wall cabins consistently outlived unbraced equivalents by 30 to 50%. A typical unbraced cabin required major reconstruction every 5 to 7 years. A braced cabin lasted 10 to 12 years before needing equivalent work. The difference was structural integrity preventing accelerated decay. Fewer rebuild cycles meant higher operational continuity. A trapper, homesteader, or section house crew could occupy the same structure across multiple seasons without interruption. The economic value was substantial. Every reconstruction consumed materials, labor, and time. Eliminating one rebuild cycle in a decade saved weeks of work. Final artifact evidence appeared in an 1884 inspection note. Door frame sound, center post tied to plate. The inspector recorded what remained functional after winter. The spine wall was still performing its intended function years after installation. Closing reflection focused on principle rather than individual innovation. The frontier tested every assumption. Structures that survived were those that distributed loads efficiently. Thickness alone was insufficient. Connection method determined performance. A properly braced thin-walled cabin outperformed an improperly connected thick-walled cabin under identical conditions. Survival favored load sharing over brute thickness. The principle applied to structures, supply lines, and communities. The isolated failed. The connected endured. The spine wall demonstrated what engineering knowledge could accomplish with limited materials and simple tools. One hewn post, correctly positioned and tied, converted a vulnerable shelter into a structure that weathered decades of mountain storms. Strength came not from heavier logs, but from a load shared across the whole.